All right, we're going to get started again. So hopefully we can bring up the next set of slides. Welcome back from the coffee break. Our next speaker is Professor Cyril Parnet, who is from the University of Edinburgh in Scotland. He's going to be talking about inferential brain mapping. Thanks.
Hi there. So the talk today, I want to focus on statistical inference. So inference by itself is the process of deducing properties of a distribution. And inferential statistical analysis infers the properties about the population, so that's about deriving estimates and also testing hypotheses. And what I'm going to focus on today is going to be about deriving good estimates from your GLM. So the standard way you would analyze your data is a GLM, but how can we improve it so that the estimates are more likely to reflect the true neural response? And it has implication whether you do univariate or multivariate statistics. And then for the rest of the talk, I will focus on what we can do for multivariate statistics, so related to all the talks we have this afternoon about MVPA and RSA and so on. And for this, you also have to have to consider different things related to your design, the way you would prepare your experiment. That's going to influence the estimates you're going to have, and that's going to bias or not your multivariate statistics, whether it's MVPA or RSA. And I will finish by multivariate hypothesis and inference. So again, once you build good estimates and you create your supervector machine or your RSA, then you want to infer something, and the nature of this inference, what you might think you do by looking at multiple voxels together. Just to start is a reminder of what the kind of variance we are talking about when we look at functional MRI data. We can distinguish different levels, and so we have the variations from trial to trial, and so that's the first one I want to address, which is basically an issue of modeling. So which kind of model you're going to input in your GLM so that you can have good estimates. Then we have the variations between voxels, and so that's going to be issues related to MVPA or to connectivity, an issue of the spatial covariance. And then, of course, we've got the variations between subjects, which is the random sampling and the directionality of the effect, which, as we will see, has some impact about what you can infer from, say, MVPA when it comes to directionality of effects. So let's start by deriving good estimates from your GLM. So the first thing you want to do beside your experiment is at the same time to account for neural differences from trial to trial. And so in many tasks, your subjects have to take a decision. And what we know from neurophysiology is that all these works point to what we call accumulation models, in which the neuron fire until enough information is accumulated. And this implies that the decision-related areas have different neural dynamic from trial to trial, because the neurons, just from the different information, they will fire at different, for different duration. And which, in this case, we want to have a model which says, okay, this is trial 1, this is trial 2, and so on, but at the same time, we want to somehow be able to account for these differences in neural firing rate and duration. And so, in 2008, Greenbund and Martin, who's going to do the next talk, they introduced the idea of using variable impulse models and variables versus variable epoch models. And so your variable impulse is the usual stuff, which is you do your GLM and you put a parametric regressor, which means we're going to have modulations of the amplitude of a signal. And what Greenbund and Martin showed is that the variable epoch model, so what you do is you use the stimulus duration, and in this case, for instance, you would take the reaction time of your subject, so instead of saying, let's convolve with a stick function, so well, each time we put the actual reaction time and convolve this. So that creates tiny differences in the shape of your GLM. Okay, so for each trial now you've got tiny little changes in shape, but that gives too much better prediction for those areas. Of course, one issue with that is that the variable epoch model is going to mismodel the regions which have no trial-to-trial variations. And so in one hand, it's good for those regions where we have these changes, so you simply put the reaction time not as a parametric regressor, but as simply the duration of each event equal your reaction time, but then you don't have a good detection in other areas. And so the solution we are coming up with is to basically to model these variations is to use first the mean reaction time across all your trials and conditions. And so that's a very general way to do it. So what you do is you set up your experiment, you measure reaction time, and instead of convolving with a stick function, you simply compute the mean reaction time across every single condition, and now that becomes the duration of your neural event, and then you add the parametric modulation on top of that. And that minimizes the difference between regions where we have variations and regions when you don't have variations. You can also add some of basis functions, so I saw that we have a poster on that. And that captures all the variations, and that also allows you to get better beta estimates once you correct basically your estimates. So here is an example of a response for which we have variable neural duration. And so each time, at each trial, the neurons, we simulate neurons which have different duration, and that creates these changes in the mnemonic response function. And that's your traditional fMRI when you do an HRF with a parametric regressor. So that's the issue when you do just a standard GLM. It's because you're going to minimize the mean square difference, and here, because the duration of neurons is a bit longer, we have this shift. So we can see the neural response is shifted compared to your onset of a trial, and that's because the neurons have different duration when they fire. And so that means that we're just not going to capture the top, and you end up mismodeling. And so basically now your beta, if it's there, whereas you wanted it to have a much higher value. So once you're going to compare two conditions, you don't really know if it's a difference because you mismodel the data or if it's an error because there's a true difference. So now we can use the true reaction time. So that's what Martin did. We see it fits well the data. And our approach is to say, well, what we can do instead, and that gives actually better results, is to use the HRF with the derivative and the mean reaction time. And so we take the mean reaction time, and then we add the parametric regressor on top of it. And we can see we got pretty much the same thing as the green one. So it's a much more general and flexible way to analyze your data, because now you can derive very good beta estimates, and you can contrast across multiple conditions without any problems. Another aspect about estimating single trials is that the slow event-related design are inefficient. So when you do in terms of GLM, and also because the number of stimuli, of course, is limited because you're super slow, and because also it's not very natural for your subject. And so instead, you want to use other type of designs which are much more efficient. So for your fast event-related design, typically in GLM you would use stochastic design. And so the probability of events over time is changing, and so that you maximize your detection. So in this work, what Janet showed is when you want to derive estimates, so you want to get beta parameters, whether it's to do your maps or to do MVPA or RSA. And so what we have here is the ISI between your stimuli. So you go from a very fast event-related design to a slow one. And so the first result is to say, okay, it doesn't really matter, so you can do fast, that's fine. And the other aspect to look at is basically the different level of noise as well, and to look at which way we're going to compute the betas. And so typically, when you want to do a super vector machine or representational similarity, you want to have one beta per trial, right? And so what we do is we set up a big design matrix, and in this big design matrix, we put one trial, we put one regressor per trial. And so that builds this kind of matrix there. And so that means each trial is modeled by one response. And so we've got one beta per trial, that's what we want, and then we can input that into, say, a super vector machine. And now what she found is that What works best is to actually not create one design, but to create many, many, many designs. And so what you do is you set up, this is your least square solution all versus least square solution single. And so you tested plenty of other techniques, but least square, so basically what you already have in any of the packages to analyze the data. The only difference is that now if you have 100 trials, you need to do 100 GLMs. Okay, so GLM1 would be trial 1, followed by all of the other trials. And then, so you got 100 trials, you do 100 GLMs. And so when you do that, what we can see is that the beta estimates that you get are much more stable across the different, whether it's fast or if it's slow event-related design, and it also less biased in terms of, well, because it was simulation, so she found that it was less biased and find the better estimates. And so you have now a very simple way, which is to say, well, first you want to use the mean reaction time plus a parametric regressor, and then you want to build one design per trial. And so that was going to give you a very good estimates for that particular trial. And then you do that for all of your trials, and then you can input it into your super vector machine or representational similarity analysis. So what kind of, so that's about getting the right measure, the right beta. And so that's important because, of course, if we don't have the good estimates, we can think we have differences between conditions, and this has to do with the fact that we didn't model well the data rather than true differences. Once we've got that, another aspect I want to talk about is, before getting this data, is what kind of errors we can make by building wrong designs, and how it's going to influence these beta estimates. And so typically for multivariate analysis, the first thing we want to ask is how many stimuli to put in your experiment. And so in classification, so super vector machine or Gaussian process, they are more accurate with limited number of classes. And so if you know you want to, this is the kind of technique you want to go for, you want to do classification because you want to separate patient A versus B, or you want to separate, cars versus houses, then you're going to use a super vector machine. And so in this case, you want to use multiple exemplars per class and category, but a limited number of classes. What's important is also to always have the same number of stimuli to avoid the bias toward the most frequent stimuli. So if you want to compare houses versus faces, well, you want to make sure that you've got as many faces and houses so that you can derive good estimates to input into your super vector machine. Now, if you do representational similarity analysis, that necessitates what Nico called a stimulus-rich design, and it's not limited to the number of classes. So in this case, you will go for as many classes as you want, but what's important is to use non-repeated stimuli. So in the classification example, you actually want to limit the number of classes and possibly repeat a few times the same stimulus, whereas in RSA, it's completely the opposite. You want to do plenty of classes, and you also want to have plenty of non-repeated stimuli. So it means by construction, depending on what analysis you want to do, that's going to change the way you're going to present the stimuli to your subject. Now, which order for your stimuli? Well, as I was saying, for univariate analysis, typically we use a dynamic stochastic design, or also called pseudo-random, because it offers maximum power. And so that's where the probability of stimuli changes over time. So let's say you have two conditions. You start with a lot of condition A, a little bit of B, and then it changes, a lot of B's and less A, and then you keep rolling. One issue is that with large number of classes, of course, the spacing becomes very large, and so it gets close to the noise. And what Janet shows as well is that for multivariate analysis, only randomized designs are appropriate. And so basically, if you do an experiment, you do your fast event-related design, and you use stochastic designs because you know you're going to maximize power to detect when you do a GLM for univariate analysis, well, basically, that's you stop. You can't really do multivariate analysis if you use a stochastic design because there is a bias. And so what it means that you need now to design an experiment knowing whether you're going to do univariate or multivariate. Because you can't have both and have like maximum detection power for both at the same time. So you have to choose really what kind of analysis you're going to go for, and that's going to influence your design. And so the optimal univariate or multivariate designs have different requirements. And so similar kind of plots, what we can see here. So again, we have the least square single and the least square all. So we know already the least square single, that is to build one model per trial, is the best way to go. And we also compare within exemplars or between exemplar pairs. We have multiple kind of designs. So we've got the block, we've got the alternative, and the completely random. So alternating is this stochastic design, which is we know is the best for univariate analysis. And so for random similarity analysis, the pseudo-random design, we can see that it leads to artificial differences, which means basically what you want to do is alternating and random designs are better. And interestingly, it didn't really matter what ISI you are using. And so again, it means you can't really use pseudo-random designs because you don't have, well, the differences are not real, so it creates a bias. The reason is because what you have is trials which are spaced very close together, and so you accumulate information on top of each other, and that creates a bias in the covariance. And so that's why you can't use these designs to do multivariate analysis. They are very, very good for univariates, but they create a bias in multivariates. Again, how many runs you want to do in your experiment, that's going to influence the result. Again, any collinearity or autocorrelation bias your results in multivariate pattern analysis. And so it means that what you want to do is to run correlations and cross-validation between the runs, which are better than if you split. So if you say you acquire the data and then you split half of the experiment and you say I'm going to analyze the data this way, I'm going to use or leave one out, it's actually much better to use cross-validation between runs than to split the data within runs. And so again, we can see some differences in this graph. So again, we've got the least square single versus least square all, different type of designs and ISI, and we can see that there is some bias for the within, so on these ones there. Okay, so that's why you need to run your cross validation between runs, and you can't leave one out. Is not a very good option. So the take home is simply that it's better to get 4 times 100 volumes in 4 sessions than 1 time 400 volumes. And so that's true for MVPA, and whereas it's not true for basically univariate GLM. So again, depending on what technique you want to use, you've got an optimal choice to make in terms of design. A word on the confounds, specifically for multivariates. And so this one is a little bit tricky because what we used to do is always to counterbalance, right? And so you got your subjects and you say, well, so we're going to do ABC, CBA, you know, that's fine. And so what it is, why do we want to counterbalance? Well, when we counterbalance, we assume there is multi-directional effect. So let's take learning. So you do ABC, and so you balance with CBA. Now, when you do univariate analysis, if you test the difference between A and C, there is no confound because, of course, we balance the different subject. And so it's cancelled out basically using the averaging. Now, in multivariate analysis, the issue is that we use the mean accuracy, for instance, of your MVPA, of your supervector, or a correlation. And this is confounded because the effect that you have, and it's true for each subject, is not cancelled because now we don't have a direction of the effect anymore. Right? When you do a t-test or you compute your contrast A bigger than B, well, it's going to be either positive or negative. Now, if you do an MVPA and you get an accuracy, you say, well, it's 80% accuracy, you don't have any directionality. And so which means if you do 10 subjects, they can all have 80%, except that for 8, for half of the subject, A is bigger than C, and for the other half, it's C who's bigger than A. And so, sure, we can decode it, but the directionality is completely lost. And so it has some implication about what you can infer, because you completely lost the directionality of the effect. And so also for representational similarity analysis, another important aspect is that you need to ensure a full design balance. And because you're going to create these matrices in which we put every single trials for every single conditions to do the representational similarity matrix. And so now, if you only have two types of designs, so ABC is just the opposite of CBA, and so basically what you have is symmetric designs, and you have symmetric random similarity matrix. They're simply reverse mirror one from each other. And so to make sure you don't have a bias, now you need to also do all of the other possibilities, which is to also use ACB, BAC, BCA, CAB, CAB. Okay? And so if you want to do RSA, again, it will influence the way you're going to do, you're going to create your experiment and the way you're going to counterbalance across subjects. Now just to finish, multivariate inference. So what kind of inference we make by using multivariate pattern analysis? So we are testing for patterns. But what's really we can see is that if all the voxels show very small effect, so what you have is a true univariate effect, A is bigger than B, but it's tiny. Then basically your classifier is going to be significant. So you don't find anything with your standard mass univariate approach, but you can find something with your multivariate analysis, even though all you have is a very unidimensional effect. And so the pattern is not really to be understood as a pattern as we traditionally see it in the papers. And so, you know, this is the standard way to represent the data. We say, well, this is voxel 1, this is voxel 2. And then we can do the univariate analysis. We find this one, and we can find this one. And of course, we say, well, with multivariate analysis, what we can do is the difference to create a plane which is going to separate the two conditions. But often what we do when we do MVPA is that the inference is say, well, we have a multivariate. We think about the data as multivariate, as multiple dimensions, as something like that, which has two dimensions on the right. But really, what we have in the middle is just univariate in the sense that we can see that, for instance, the red ones are always a little bit higher than the blue ones. So it's just an univariate and a single dimension. If you do an SVD on this, there's absolutely nothing. It's just one big vector which separates the data. And so it's an univariate effect, but you only detect it using a multivariate techniques because it pulls the information by plenty of voxels together. So it's much more sensitive to detect very tiny changes. And so in a sense, you detect an univariate effect, the same as what you would do with a GLM, but simply the techniques are more powerful in terms of detecting those effects. And so your linear classifier typically will take advantage of the small yet consistent differences in mean activations. It doesn't mean that's always what you have when you do MVPA, but that's one possible it's something which is possible. So you think you have differences which are multivariate or multidimensional, but really what you have is a simple unidimensional effect. And so that changes completely the way you want to interpret your results. And so in terms of interpretation, again, in terms of pattern differences, the question is, okay, I'll do a GLM, I can't find any differences, I do an MVPA and I can find difference. And so the inference I make is to say, well, because I find differences in terms of patterns, it means it's a distributed process because it's distributed over plenty of voxels. And so what David showed is that, as I was just talking in the previous slide, MVPA strives on variations between voxels, even for unidimensional differences. And so when there is something very simple to do, we can follow Courtin's kind of step-by-step way to look at this. But the key in this is to remove across voxel the means at each time point, and that ensures that the response is driven by the variance and not by the mean difference. So in the previous slide, we can see that the MVPA or the linear discriminant function will find a difference, even though it's univariate, because there is a tiny mean difference for every single voxel. So you pull them all together, and your linear discriminant function finds that it's significant, whereas you don't find it with your standard GLM. And so now if you remove across voxel the mean, then you know that it's definitely going to be something which is distributed in variance and not a simple unidimensional effect. And so you want to compare the results with or without removing this mean. And the last thing I want to talk about is the notion of sparsicity versus selectivity. So again, when we do a multivariate statistic, usually we say, okay, it's distributed, and then we also say, well, for instance, it's sparse. Or, you know, these voxels were not selective, or they are selective. And it's often used also very interchangeably, but it's not. And so for that, I would refer to now a relatively old paper from Foldiak, so we assume the multidimensional nature of a signal in a set of regions, and what really we have is that the selectivity is a property of neurons, and so we can say, well, the selectivity is going to be a property of our voxel, and the sparseness, this is encoded, it's a property relative to the stimuli and not to the voxel. And the way you can think of it is simply to look, so that's from his paper, so he's talking about cells, but we can just apply the same way in terms of reasoning about voxels. And so what we can see in this, if this pointer works, okay, so we've got the stimuli and we've got the cells, so substitute cells by voxels. So now you have a region, you do your MVPA, you've got plenty of voxels, and so these voxels are there at the top, and we've got the different stimuli that you tested are encoded on the right. And then you say, so we can put different weights, so that's going to be the weights of your support vector, for instance, rather than 1 and zeros. But and the way you're going to interpret it is to say, well, we can see, for instance, here, very selective on the left for the 1, 2, 3, and they're very selective because they respond only to stimulus 9, for instance. So that's why it was a grand mover cell, because it responds, so in your case, your voxel responds only when I present that stimulus, it has a strong weight. It doesn't have any weights, or the weights are very low when I present other kind of stimuli. And so that means it is a very selective, but at the same time, we can see across all the voxels that many voxels respond. And so that's where it's dense, whereas sparsicity has to do with the fact that only few voxels respond, but you can be sparse and yet have a broad response. Because when you look at a given voxel, this voxel responds for plenty of stimuli. And so it's important not to confound these two notions of sparsicity and selectivity, which are usually used in many papers in kind of interchangeable way, but really you read this kind of metrics, it's the marginals which matter, so that you read either in the direction of the voxels or the direction of the stimuli. And so you can obviously you apply this to your voxels. So the take-home message here is to say, well, modeling in terms of GNM is not as trivial as we might think. There's still a lot of work to be done in terms of modeling, and mismodeling will lead to create or obscure your MVPA differences. And so it's important to, for instance, use the mean response time rather than just using a standard stick function. Additionally, use parametric modulations and basis functions. You also want to estimate using not all the stimuli, all the trial in one design matrix, but to create as many designs so that you can have one beta estimate per trial. You also want to optimize your designs for MVPA, so the optimization that has been worked out for many years for the GNM as mass univariate. Well, now what we see is that there's also ways to optimize your designs for multivariate analysis, and these are not the same way to optimize your design. So if you optimize for mass univariate, you're going to create biases for multivariate analysis. So it's like you have to choose what you want to do before acquiring the data, what kind of analysis you're going to go for, what are your hypotheses, and that's going to influence your design. And so basically you won't have the best GLM and MVPA in the same design. It's not possible. So basically, you have to choose what you want to do. And of course, you also have to carefully interpret your results using additional tests for dimensionality, such as the algorithm proposed by Courtange, looking at removing the means, for instance, and also looking for differences between sparsicity and selectivity. And so you can find all of these in the references, so you can download the talk, and basically, I would say, so I put like a minimum set of references, and I would really encourage anybody to read these ones, and that's going to give you like the keys on how to optimize your designs for multivariate analysis. Thank you.